A main beam of 3 meter length span with clear span of 2.8 meter. The beam support a flooring system which exert a long duration loading of 3.9 kN per meter, including its own self-weight over its span. The beam is supported by 50 mm wide walls on either side. Carry out the design checks to show that 70 times 190 mm deep sawn section of strength group 4 timber at 90% of moisture content with standard grade. Loading applied on the beam is 3.9 kN per meter. Modification factor needed for the checking is table 5, K1. This is for duration of loading. It is long term, so it's equal to 1. For load sharing system, there is no load sharing, so K2 is 1. For the bearing is 50 mm but located less 75 mm from the end of the member, so K3 is 1. There is no notch at the end of the beam, therefore K4 is 1. The beam is rectangular cross section, K5 is 1. And the depth factor for depth less than 300 mm, the K6 is 1. We refer to table 4, wet and dry grade stress for various strength group of timber. We focus on SG4, this is the for strength group 4, dry condition and standard grade. So we focus on all STD. Okay. Our bending parallel to grain is 13.2. Our compression perpendicular to grain is 1.65. Shear parallel to grain is 1.23 Newton per millimeter square and 7,600 for E minimum. First, we check the bending for the beam. We calculate the applied bending moment equal to WL to the power of 2 divided by 8. So L is the effective lag. Our applied bending moment is 3.96 kN meter. We calculate the section modulus by BH to the power of 2 divided by 6. The applied bending stress is calculated as M divided by ZXX. Therefore, applied bending stress is 9.4 Newton per millimeter square. For permissible bending stress, V times bending, this is obtained from the table, times with all modification factor, K1, K2, K5 and K6. So we get 13.2 Newton per millimeter square. We compare applied bending stress with the permissible bending stress. The bending stress is satisfactory since a permissible bending stress is more than applied bending stress. We check the shear stress for the beam, calculate the applied shear force by WL E divided by 2. So W is our UDL times with the effective length divided by 2. We get our FV is 5.56 kilonewton. Then to get the shear stress is 1.5 FV divided by A. Okay. So we get 0.627 Newton per millimeter square. Permissible shear stress is then calculated as shear stress parallel to grain divided by times with the modification factor K1, K2 and K4. we get 1.23 Newton per millimeter square. Our shear stress is satisfactory because our permissible shear stress more than applied shear stress. Next, we check the bearing. Applied load FV is 5.56. Therefore, applied bearing stress is P over A bearing. So A is the contact surface. We obtain 1.59 Newton per millimeter square for applied bending stress. Permissible bearing stress is calculated as compression perpendicular to grain times with modification factor K1, K2 and K3, we get 1.65 Newton millimeter square. Our bearing stress satisfactory because our permissible bearing stress is more than applied bearing stress. Now we check lateral stability of our beam. We calculate actual depth to breadth ratio of our beam is 2.71. We refer table 7 for maximum depth to breadth ratio from the condition where the end of the beam should be held in position like in this figure. The value from the table is 3. Now we compare our H over B allowed with the H over B actual. So H over B allowed should be more than H over B actual. For the deflection, we have to calculate what is the deflection due to the bending and what is the deflection due to the shear. Formula for deflection due to the bending at midspan is 5 WL to the power of 4 divided by 384 EI. So we solve this and we get 11.02 millimeter. For deflection to the shear, we use 19.2 M max divided by AE. So we get 0.75. So the total deflection is deflection due to the bending plus deflection due to the shear. So we get our total deflection is 11.77 millimeter. To calculate the permissible deflection, that's mean allowable deflection for the beam, is 0.03 LE. So we will get 8.55 millimeter. We compare our permissible deflection with the total deflection. See here, our permissible deflection is less than our total deflection. Therefore, the deflection is not pass. We need to redesign by increasing the size of beam.